genetic code, the Krebs cycle, and ATP, chemiosmosis is universal to all life and appears to have been a property of the last universal common ancestor, Luca. Martin and Russell explain why. In the broadest of terms, chemiosmosis is the movement of protons over a membrane, hence the resemblance in name to osmosis, the movement of water over a membrane. In respiration, what happens is this. Electrons are stripped from food and passed along a chain of carriers to oxygen. The energy released at several points is used to pump protons across a membrane. The outcome is a proton gradient over the membrane. The membrane acts a bit like a hydroelectric dam. Just as water flowing down from a hilltop reservoir drives a turbine to generate electricity, so in cells the flow of protons through protein turbines in the membrane drives the synthesis of ATP. This mechanism was totally unexpected. Instead of having a nice straightforward reaction between two molecules, a strange gradient of protons is interpolated in the middle. Chemists are used to working with whole numbers. It's not possible for one molecule to react with half of another molecule. Perhaps the most confounding aspect of chemiosmosis is that fractions of whole numbers abound. How many electrons need to be transferred to produce one ATP? Somewhere between 8 and 9. How many protons? The most accurate estimate yet is 4.33. Such numbers made no sense at all until the intermediary of a gradient was appreciated. A gradient, after all, is composed of 1,000,000 gradations. It doesn't break into whole numbers. And the great advantage of a gradient is that a single reaction can be repeated again and again just to generate one single ATP molecule. If one particular reaction releases 1/100th of the energy needed to generate one ATP, the reaction is simply repeated 100 times, building up the gradient step by step until the proton reservoir is big enough to generate a single ATP. Suddenly, the cell can save up. It has a pocket full of small change. What does all this mean? Let's go back to the reaction of hydrogen with carbon dioxide. It still costs bacteria 1 ATP to get the ball rolling, but they are now able to generate more than 1 ATP as they can save up towards a second ATP. Not a good living, perhaps, but an honest one. More to the point, it makes the difference between the possibility of growth and no possibility of growth. If Martin and Russell are right, and the earliest forms of life grew from this reaction, then the only way life could leave the deep-sea vents was by chemiosmosis. It's certainly true that the only forms of life that live from this reaction today both depend on chemiosmosis and can't grow without it. And it's equally true that almost all life on Earth shares this same curious mechanism, even though it's not always needed. Why? I imagine simply because they inherited it from a common ancestor that couldn't live without it. But here is the chief reason to think Martin and Russell are right: the use of protons. Why not, for example, charged sodium, potassium, or calcium atoms, which are used by our own nervous systems? There's no obvious reason why protons should be preferred to a gradient of any other type of electrically charged particle, and there are some bacteria that generate a sodium gradient rather than a proton gradient, albeit rarely. The main reason, I think, goes back to the properties of Russell's vents. Recall that the vents bubble alkaline fluids into an ocean that is made acidic by dissolved carbon dioxide. Acids are defined in terms of protons. An acid is rich in protons, an alkali poor. So bubbling alkaline fluids into acidic oceans produces a natural proton gradient. In other words, the mineral cells in Russell's alkaline vents are naturally chemiosmotic. Russell himself pointed this out many years ago, but the realization that bacteria simply could not leave the vents without chemiosmosis was one of the fruits of his collaboration with Martin, who looked into the energetics of microbes. And so, these electrochemical reactors not only generate organic molecules and ATP, they even handed over an escape plan, the way to evade the universal 10-pound note problem. Of course, a natural proton gradient is only of use if life is able to harness the gradient and later on generate its own gradient. While it's certainly easier to harness a pre-existing gradient than it is to generate something from scratch, neither is straightforward. These mechanisms evolved by natural selection, there is no doubt. Today, it requires numerous proteins specified by genes, and there is no reason to suppose that such a complex system could have evolved in the first place without proteins and genes composed of DNA. And so, we have an interesting loop. Life could not leave the vents until it had learnt how to harness its own chemiosmotic gradient, but it could only harness its own gradient using genes and DNA. It seems inescapable. Life must have evolved a surprising degree of sophistication in its rocky hatchery. This paints an extraordinary portrait of the last common ancestor of all life on Earth. If Martin and Russell are right, and I think they are, she was not a free-living cell, but a rocky labyrinth of mineral cells, lined with catalytic walls composed of iron, sulfur and nickel, and energized by natural proton gradients. The first life was a porous rock that generated complex molecules and energy right up to the formation of proteins and DNA itself. And that means we have only followed half the story in this chapter. In the next, we'll consider the other half, the invention of that most iconic of all molecules, the stuff of genes, DNA.